Hi guys, welcome back to another physics video. This is Akshata and I am part of KARMANT Learning, which is a wonderful non-profit organization. Today's video is about projectile motion. So remember how we covered motion in only one direction? This time it features motion in two directions, the x and the y axis. So let's get started. So basically, projectile motion involves objects that are either launched or thrown. So it can be like an object that is thrown off a cliff. So it has both vertical motion and horizontal motion, since it's moving both up and to the right. So our y-axis is involved as well as our x-axis. I know that both x and y direction at the same time can be pretty confusing, but it's important to note that the x and the y direction are both independent of one another. And another key thing to note is that in any situation, when an object is launched or even thrown, like let's say a ball is being thrown off a cliff in situation A, and then a ball is being thrown from the ground in part B. So in both cases, the x direction of the motion has no acceleration at all. Instead, the y direction of the motion faces an acceleration of g, which is a downward 9.8 meters per second squared. If you've forgotten what acceleration was, I would advise that you look back at some of the previous videos. I explained it there in more detail. So basically, this acceleration causes a change in our y velocity. So this may seem still a bit complicated having both x directional motion and y directional motion at the same time, so I'll break it up. So in this case, let's say somebody's kicking a ball from the ground. So at time t is equal to 0, the ball is at the ground. It hasn't been kicked yet. So let's say at time t is equal to 2 seconds. The ball is right here. So you can see that it's gone some distance in the x-axis and some distance on the y-axis. So it has gone both to the right and vertical. I'm just going to go over briefly what each of these equations means. So in this case, the first equation describes us obtaining the final velocity from velocity initial plus the product of acceleration of the object multiplied by time. So basically this one gives you the final velocity. And in the second equation, we get the change in displacement, which is a product of the average velocity multiplied by time. And our third equation is also one for delta x, except it's in different terms, this time with the initial velocity and acceleration. And our fourth equation gives us the final velocity, the initial velocity plus the product of the change in displacement multiplied by acceleration. So now that we've looked at our basic kinematic equations, as I mentioned before, projectiles involves both an x direction and a y direction for movement. So like if a ball was kicked, it would go both this way and this way in some proportions. The kinematics equations branch off. So all of these kinematics equations you see are basically the same as the ones I talked about before, but they're just tweaked to make them x direction ones. So if you see here, we have the velocity in the x direction and the change in x displacement. So these can only be used to solve for stuff in the x direction. Similarly, we have the same thing adapted for y direction motion. So in this case, we have our final y velocity, and then we have the change in y, or the height. And if you notice, we have our variable g here, which is not present in the first one. And this is the acceleration due to gravity, which is downwards. Breaking up these equations into two different categories is something that you'll find really helpful once you're solving these problems. Both of these are independent of one another. Okay, so I know this is getting to be a lot, and I keep stressing that the x and the y direction are different, so I just want to do a quick recap. So our x direction motion features a constant velocity. So whatever our initial velocity is will also be our final velocity, but only in the x direction. And this is only because there's actually no acceleration. So also, in the y direction has changing velocity because of this value of g, and it has a constant acceleration downwards. Since both of these x direction and y direction are independent of one another, The time variable is something that helps to solve for both, and I'll go into that in more detail. So now that I've gotten into some basics for projectile motion, you may be wondering what these problems might look like. So I think it's best to start off with a hypothetical situation of someone throwing something off a cliff. So let's say this person is going to throw a ball off this 10-meter tall cliff. So you may be asked to find how long this object stays in the air before it hits the ground. Another thing is the initial speed, which is the ball is thrown at, or the maximum height the ball reaches. So there's a lot of things that you could be asked. One thing that is really important to even get started with projectile motion after the equations is the components. So if you remember back in the equations that I showed you, there were terms such as Vx and Vy. And that basically means velocity in the x direction and velocity in the y direction. You might just be given a single velocity, like 10 meters per second. How would you find velocity in the x and y direction? So in order to solve problems like these, we have to treat each direction separately, and this actually involves components. So you may have heard of components before, and if you do, you know that they involve some amount of trigonometry. So let's say you're given a basic velocity of 10 meters per second, and they happen to give you an angle that it is traveling at 30 degrees. So from this, you're neither given x nor the y velocity, but you have to find both of them. So one easy way to find them is to use the triangle method. So we are given our hypotenuse, which is 10. We have to find our components. So we have to find our y component of the velocity and our x component. To do that, we just have to turn it into a triangle and fill out the values using simple trigonometric terms. So let's say we have sine 30 is equal to the opposite over the hypotenuse, right? From SOHCAHTOA. To solve for the opposite side, which is also the y component here, we just have to isolate it. So we can get opposite is equal to h times sine 30 degrees. So just by multiplying our velocity times the sine of the degree, we are able to get our y velocity. This is also similar for our x velocity too. But instead of sine, we're going to solve for the adjacent. And we use cosine for that. So we use cosine 30 degrees is equal to adjacent over hypotenuse. And remember, this is the x component. And to do so, we just set cosine 30. And this gives us our x velocity. I think this diagram is really useful in visualizing the whole process. As you can see, here's our initial velocity vector. We have been given our angle of launch, theta. We can get the x component from v0 cosine theta, and we can get the y component from v0 sine theta. So I know we've gone over a lot of new things, but I just wanted to cover some ground on some strategies that you can use when solving problems. So first, I would recommend you assess what type of problem you have. Are you solving for the time? Are you solving for the distance your object travels? Next step I would advise is to write down your knowns and unknowns. This is similar to how we made a knowns and unknowns list before. And also, then you would figure out which equations you would like to use. I recommend consulting your list of x direction and y direction equations. So now we're going to go over a basic practice problem. So one of the most common types of problems you're going to see is to solve for a distance that a projectile travels. So the example included here involves a person that, once again, throws a ball off a cliff with a horizontal velocity of 20 meters per second. So here's the ball. And the cliff is 100 meters tall. So what's the distance the ball hits the ground from the base of the cliff? So what should we do first? We're solving for something in terms of distance. Here we're solving for horizontal distance. So now let's make a knowns and unknowns list. So the stuff that we know is the initial height, which is 100 meters, and we know our initial velocity, 20 meters per second. There's also one more thing that we know, that the acceleration due to gravity in the y direction, so AY, is equal to negative 9.8 meters per second squared. We don't know the time that it takes for the ball to hit the ground. We also don't know the distance it travels in the x direction. So based on our knowns and unknowns list, we're going to select a few equations. So first, we want to solve for something that has time involved, because we don't know that. Most of the quantities are in the y direction. So let's look at a y direction equation first. So to solve for the time, we can use this equation, and then to get the distance traveled in the x direction. So judging by the knowns and unknowns list, for the x direction, this equation would be the most suitable. Our first step to solve the problem would be to break out the x and y components of the initial velocity. Our initial velocity is like this, 20 meters per second. So here there is no y component in the velocity because it's all horizontal. So our Vy0 would be 0 meters per second. But there is an all horizontal velocity. So that makes our Vx0 20 meters per second. The first equation we picked out was in the y direction, intended to solve for the time. So we know our initial y height, which is 100 meters, and we know our initial y velocity, which is 0. So our equation just becomes y is equal to negative 1/2 gt squared. So solving for t, we get rad 2y over g. Now that we have our time variable solved for, we can use it in our second equation for the x direction from the base of the cliff. So in this case, our velocity is constant throughout. So that means that our average velocity is the same as our initial velocity, v0 times t. So if we substitute this t expression for t, we get x is equal to v0 times root 2y over g. I recommend substituting all the numbers and values after you solve for everything algebraically. We get that x is approximately equal to 90.35 meters from the base of the cliff. So that's all I have for this video. Thank you so much for watching. If you like this video, please like and subscribe to our channel, and hit that notification bell for more future videos. If you have any questions or suggestions, please email info@karmantlearning.org.